I heard the story more than once, and never exactly the same way twice, which is usually how you know a story is true. Werner Heisenberg told it to me himself years later, though by then he'd smoothed the edges of it into something almost gentle. Others who were in Copenhagen at the time told it differently, colder, sharper, with more silence in it. But everyone agreed on one thing. For a period of weeks in early 1927, two of the greatest physicists alive were barely speaking to each other, and the reason had nothing to do with politics or pride or anything petty. It came down to a single question neither of them could let go of. What does it actually mean to know something about a particle you cannot directly see? To understand why this nearly broke them, you have to understand what Copenhagen was in those years. Bohr's Institute wasn't just a laboratory. It was closer to a monastery for a very specific kind of obsession. Young physicists came from all over Europe to sit in Bohr's seminar room, sometimes for years, arguing over ideas so abstract that most of the outside world had no language for them. Heisenberg had arrived there in 1926, already famous within the field for having built the year before an entirely new mathematical formulation of quantum mechanics, matrix mechanics. He called it, while recovering from hay fever on the island of Helgoland. He was 24 years old. Bohr was in his early 40s, already a towering figure, the man who had explained the structure of the hydrogen atom over a decade earlier and effectively founded the entire field Heisenberg was now working in. The two of them respected each other enormously. That's important to say clearly, because what happened between them wasn't a falling out over ego. It was something rarer and, in a way, more serious, a genuine disagreement about the deepest layer of physical reality between two men who each believed the other was making a real mistake. The problem began with a question that sounds almost simple, stated plainly. Can you know, at the same time, exactly where a particle is and exactly how fast it's moving? Classical physics never had to ask this question seriously. Of course you can, classical physics says. A ball has a position and a velocity both at once, whether you're measuring them or not. The whole edifice of Newtonian mechanics depends on that assumption being true. But Heisenberg had been working through the mathematics of the new quantum theory, and he kept running into something that troubled him. In his matrix formulation, certain pairs of physical quantities, position and momentum chief among them, didn't behave the way ordinary numbers behave when you multiplied them. If you took the momentum of a particle and multiplied it by its position, you got a different answer than if you multiplied position by momentum first. In ordinary arithmetic, of course, 3 times 4 and 4 times 3 give you the same result. In Heisenberg's matrices, they didn't. The order mattered. The two quantities, in a mathematical sense, refused to commute. Heisenberg understood this was significant, but for a long time he wasn't sure what it meant physically. It felt to him like the mathematics was trying to tell him something about the limits of what could be known, not just about the limits of what could be calculated. In February of 1927, while Bohr was away on a skiing trip in Norway, and I want you to sit with that detail for a moment, because it matters to how this story unfolded. Heisenberg had the room in Copenhagen essentially to himself, and alone, without Bohr looking over his shoulder, he worked out an argument that would become one of the most famous results in the history of physics. He imagined an experiment, a hypothetical microscope, powerful enough to see an individual electron, illuminated not by ordinary light but by gamma rays, because gamma rays have a wavelength short enough to resolve something as small as an electron. Here was the trouble. To see the electron with any precision, you need light with a very short wavelength. And short wavelength light, gamma rays especially, carries a great deal of energy per photon. When that photon strikes the electron, in order to be reflected back into your microscope so you can see it, it doesn't bounce off gently. It gives the electron a violent, unpredictable kick, changing its momentum by an amount you cannot fully predict or correct for. The very act of measuring the electron's position precisely disturbs its momentum. And if you used lower energy light instead, to disturb the electron less, the longer wavelength would blur your image, and you'd lose precision in position instead. Heisenberg's conclusion was that there is a fundamental physical limit to how precisely you can know both quantities simultaneously. Not a limit imposed by clumsy instruments that better engineering could someday overcome. A limit built into the structure of measurement itself. He wrote it up, sent a version of the paper off, and felt, I think, genuinely proud of what he'd found. He believed he'd identified the physical mechanism, the disturbance caused by observation, that explained why position and momentum refused to commute in his mathematics. Then Bohr came back from Norway and read the paper. What happened next is the part of the story that varies depending on who's telling it, but the substance stays the same. Bohr thought Heisenberg's physical argument, the gamma-ray microscope, the disturbance caused by the measuring photon, was flawed. Not wrong in its conclusion, but wrong in its reasoning. And to Bohr, in physics, the reasoning mattered as much as the conclusion. Heisenberg's picture implied that the electron had a definite position and momentum all along, and the measurement merely disturbed our knowledge of one while we tried to pin down the other, as if the uncertainty were something we introduced through clumsy handling rather than something already woven into the nature of the particle itself. Bohr had a different and, in his view, deeper explanation. It wasn't only about the physical disturbance of measurement. It was about the wave nature of matter itself. An electron doesn't behave like a tiny billiard ball waiting to be measured. It behaves in certain experimental contexts like a wave, and a wave, by its very mathematical nature, cannot have a perfectly defined position, because a wave is by definition spread out. To get something closer to a definite position, you have to combine many different wavelengths together into a tight packet, and the price of doing that is that the packet no longer has one clean, well-defined wavelength, and wavelength is directly tied to momentum. The uncertainty wasn't primarily a story about clumsy microscopes disturbing delicate particles. It was a story about the fundamental wave-like character of matter, something Heisenberg's version of the argument didn't fully capture. This is where the temperature in the room, by every account I ever heard, dropped considerably. Heisenberg didn't take the criticism well, not at first. He had worked the argument out carefully alone, while Bohr was away, and he believed he'd found something real. Being told, upon Bohr's return, that his reasoning was essentially the right conclusion built on the wrong foundation was not an easy thing for a 25-year-old, however brilliant, to absorb gracefully from a man he revered. The disagreement stretched on for days, then weeks. They argued long into the nights, in Bohr's office, at the Institute, walking the streets of Copenhagen. Heisenberg later described reaching a point where he simply broke down, alone in his room, in tears, not from being wrong exactly, but from the sheer exhausting pressure of being pulled apart, argument by someone whose judgment he trusted more than his own. I think what made it so difficult wasn't that either man believed the other was a fool. It was the opposite. Heisenberg respected Bohr too much to simply dismiss the criticism and move on. And Bohr respected Heisenberg too much to let an imprecise argument stand uncorrected, even one that reached, in Bohr's own view, the right final answer. Being taken seriously by Bohr meant being pushed until the reasoning was airtight, and there was no version of that process that didn't hurt. What eventually resolved it wasn't one side simply winning. It was a kind of synthesis worked out slowly that both men could live with. Heisenberg's uncertainty relation, the mathematical statement that the product of the uncertainties in position and momentum can never fall below a certain fixed value, stayed intact. That part of his work was correct, and it remains one of the true pillars of quantum mechanics to this day. But the interpretation around it broadened to include Bohr's insight about wave-particle duality, folded into what Bohr would soon after call the principle of complementarity, the idea that a quantum object has different, mutually exclusive aspects, wave-like and particle-like, and which aspect shows itself depends on how you choose to look at it. Neither description alone was complete. You needed both, held together, even though they seemed to contradict each other. By the time Heisenberg's paper was published, it carried, at Bohr's insistence, a postscript acknowledging Bohr's contribution to sharpening the argument. I've always found that detail telling. It wasn't a retraction, it was an admission on both sides that the truth had needed both of them to fully take shape. I came to know this story secondhand through Heisenberg himself years later, and through others who'd been in Copenhagen at the time. And I always thought it captured something essential about how real physics gets made. It isn't a story of one genius arriving at a clean insight in isolation. It's a story of two extraordinarily gifted men, each convinced the other was missing something important, pushing each other past the point of comfort, because neither one was willing to let an idea stand until it could survive the other's full weight of scrutiny. I thought about that disagreement often later when I was running the laboratory at Los Alamos, watching brilliant, strong-willed physicists argue with each other late into the night over calculations that mattered in a very different, much more immediate way. There's a particular kind of respect that only shows itself as friction, the kind where you refuse to let someone you admire get away with a sloppy argument, precisely because you think too highly of them to let it slide. Bohr and Heisenberg nearly stopped speaking that winter. But what came out the other side of that argument, the uncertainty principle as we understand it today, wave-particle duality bound together by the deeper principle of complementarity, became one of the load-bearing walls of everything quantum mechanics would later become. Some of the truest physics I've ever seen was built exactly that way, not from agreement, from two people who cared enough to disagree until neither of them could ignore what the other saw.